Welcome, Self-explanatory audio video book broadcast from Leader IAS and Yashas Institute. Myself, Professor Suhas Sargar. These are the broadcasts are the self-explanatory for the self-study of a student. Today, in this broadcast, you are going to learn State Board of Maharashtra, Standard 10, Medium English Medium, Subject Science and Technology, Chapter number 2, Periodic Classification of Elements. What we all going to learn in this topic? Chapters. First, elements and their classification. Second, Dobereiner's Triads, Newlands Law of Octaves, Mendeleev's periodic table, and the modern periodic table. So let's begin. Can you recall first what are the types of matter? Question mark. What are the types of elements? Question mark. What are the smallest particles of matter called? Question mark. 4. What is the difference between molecules of elements and compounds? Question mark. Classification of elements. We have learned in the previous standards that all the atoms of an element are of only one type. Today, 118 elements are known to the scientific world. However, around year 1800 only about the 30 elements were known. More number of the elements were discovered in the course of time. More and more information about the properties of these elements was gathered. To ease the study of such a large number of elements, scientists started studying the pattern, if any. In the vast information about them, you know that in the initial classification, elements were classified into the groups of metals and non-metals. Later on, another class of elements called metalloid was noticed. As the knowledge about elements and their properties went on increasing, different scientists started trying out different methods of classification. Next topic is the Dobereiner Triads. In the year 1817, a German scientist, Dobereiner, suggested that the properties of elements are related to the atomic masses. He made groups of 3 elements such as having similar chemical properties and called them triads. He arranged the 3 elements in a triad in an increasing order of atomic mass and showed that the atomic mass of the middle element was approximately equal to the mean of atomic masses of other 2 elements. However, all the known elements could not be classified into the Dobereiner triads. See the pictures of the Dobereiner's triads. Next, the Newlands Law of Octaves is another topic. Newlands Law of Octaves. The English scientist John Newlands, who related the atomic masses of elements to their properties in a different way. In the year 1866, Newland arranged the elements known at the time of an increasing order of their atomic masses. It started with the lightest element, hydrogen, and ended up with a thorium. He found that every 8th of element had properties similar to those of the first. For example, the sodium is the eighth element from lithium and both have the similar properties. Also, the magnesium shows similarity to beryllium and the chlorine shows similarity with the fluorine. Newland compared this similarity with the octaves in a music. He called the similarity observed in the eighth and the first element as the law of octaves. See, in a picture, there is a chart, Newlands octaves. Now, in a box, do you know, in the Indian music system, there are the 7 main notes, namely Sa, Re, Ga, Ma, Pa, Dha, Ni, and their collection is called the Saptak. The frequency of the notes goes on increasing from Sa to Ni. Then comes the Sa of the upper Saptak at the double of the frequency of original Sa. It means that notes repeat after completion of one Saptak. The 7 notes in the Western music are Do, Re, Mi, Fa, So, La, Ti. The note Do, having double the original frequency, comes again at the 8th place, and this is the octave of Western notes. Music is created by the variety in the use of these notes. Box closed. Many limitations were found in Newlands octave. This law found to be applicable only up to calcium. Many limitations were found in the Newlands octaves. These laws was found to be applicable only up to calcium. Newlands fitted all the known elements in a table of 7:8, that is 56 boxes. Newlands placed the 2 elements each in such boxes to accommodate all the known elements in the table. For example, cobalt and nickel, selenium and La, Ce and La. Moreover, he placed some elements with a different properties under the same notes in the octave. For example, the Newland placed the metals Ho and Ni under the note Do, along with the halogens, while the Fe, ferrous, having similarity with the cobalt and nickel. Away from them, along with the non-metal oxygen and sulfur under the note T. Also, the Newlands octave did not have a provision to accommodate the newly discovered elements. The properties of the new element discovered later on did not fit in the Newlands Law of Octaves. Mendeleev's periodic table. The Russian scientist Dmitry Mendeleev developed the periodic table of elements during the period of 1869 to 1872 AD. Mendeleev's periodic table is the most important step in the classification of elements. Mendeleev considered the fundamental properties of elements, namely the atomic mass, as the standard and arranged 63 elements known at that time in an increasing order of their atomic masses. Then he transferred these into the periodic table of elements in accordance with the physical and chemical properties of these elements. Dear listeners, these are the broadcast, the self-explanatory audio video books for the self-study of a student from Leader IAS and Yashas Institute, Navi Mumbai, Maharashtra, myself, Professor Suhas Sargar. Mendeleev organized a periodic table on the basis of chemical and physical properties of elements. These were the molecular formula of hybrids and oxides of elements, melting points, boiling points, and densities of the elements and their hybrids and oxides. Mendeleev found that the elements with a similar physical and chemical properties repeat after a definite intervals. On the basis of these findings, the Mendeleev stated the following periodic table or the periodic laws. The properties of elements are periodic functions of their atomic masses. The vertical column in the Mendeleev's periodic table are called the groups, while the horizontal rows are called the periods. See the chart of the Mendeleev's periodic table. Group 1 column, Group 2 column, Group 3 column, Group 4 column, Group 5, Group 6, Group 7 and Group 8 column. Also, the series in horizontal 1 to 12. The general molecular formula of compound shown as the R square O, R square O3, O cube, etc. in the upper part of Mendeleev's periodic table are written as R2O, R2O3, etc. in the present system. Now in a box, introduction to the scientist Dmitry Mendeleev in 1834 to 1907 was a professor in the St. Petersburg University. He made a separate card for every known element showing its atomic mass. He arranged the cards in accordance with the atomic masses and the properties of the elements, which result in the invention of periodic table of elements. The Dmitry Mendeleev's box closed. Think about it. First, there are some vacant places in the Mendeleev's periodic table. In some of these places, the atomic masses are seen to be predicted. Enlist the three of these predicted atomic masses along with their group and period. Second, due to uncertainty in the names of some of the elements, a question mark is indicated before the symbol in the Mendeleev's periodic table. What are such symbols? Question mark. The next topic is the merits of Mendeleev's periodic table. Science is a progressive. There is a freedom in science to revise the old inferences by using the more advanced means and methods of doing experiments. These characteristics of science are clearly seen in the Mendeleev's periodic table. While applying the law that the properties of elements are periodic functions of their atomic masses to all the known elements, the Mendeleevs arranged the elements with a thought that the information available till then was not final, but it could change. As a result of these, Mendeleev's periodic table demonstrated the following merits. Atomic masses of some elements were revised so as to give them the proper place in the periodic table in accordance with their properties. For example, the previously determined atomic mass of beryllium 14.09 was changed to correct value of 9.4, and beryllium was a place before boron. Second, Mendeleev kept the vacant places in the periodic table for the element not discovered till then. Three of these unknown elements were given the names Eka boron, Eka aluminium, and Eka silicon. From the known neighbors and their atomic masses were indicated as the 44, 68, and 72 respectively. Not only these, but their properties were also predicted. Later on, these elements were discovered and named as a scandium, gallium, and germanium respectively. The properties of these elements match well with those predicted by Mendel. See the table 2.4. Due to this success, all were convinced about the importance of Mendeleev's periodic table, and this method of classification of elements was accepted immediately. See the chart, actual and predicted properties of gallium. Third, there was no place reserved for the noble gases in Mendeleev's original periodic table. However, when noble gases such as helium, neon, argon were discovered towards the end of the 19th century, the Mendeleevs created the zero group without disturbing the original periodic table in which the noble gases were fitted very well. In box, use your brain power. The chlorine has two isotopes, Visa C135 and C137. Their atomic masses are 35 and 37 respectively. Their chemical properties are same. Where should these place in Mendeleev's periodic table? In different places or in the same place? Question. These are the self-explanatory audio video book broadcast from Leader IAS and Yashas Institute. Myself, Professor Suhas Sargar. Next topic is the demerits of Mendeleev's periodic table. The whole number atomic mass of the elements cobalt Co and nickel Ni is the same. Therefore, there was an ambiguity regarding their sequence in Mendeleev's periodic table. Second, isotopes were discovered long time after Mendeleev's put forth the periodic table. As isotopes have the same chemical properties but the different atomic masses, a challenge was posed in placing them in the Mendeleev's periodic table. Third, when elements are arranged in an increasing order of atomic masses, the rise in atomic mass does not appear to be uniform. It was not possible, therefore, to predict how many elements would be discovered between two heavy elements. Third, position of hydrogen. Hydrogen shows similarity with a halogen, group 7. For example, the molecular formula of hydrogen is H2, while the molecular formula of the fluorine and the chlorine are F2 and Cl2 respectively. In the same way, there is a similarity in the chemical properties of hydrogen and alkali metals in group 1. There is a similarity in the molecular formula of the compounds of hydrogen, alkali metal, means sodium and potassium, etc., formed with the chlorine and oxygen. On considering the above properties, it cannot be decided whether the correct position of the hydrogen is in the group of alkali metals, means in a group 1, or in the group of halogen in group 7. See the chart, similarity in hydrogen and alkali metals. The compounds of hydrogen and the compounds of sodium. Compounds of hydrogen include HCl, H2O, H2S, while the compounds of sodium include NaCl, Na2O and Na2S, means sodium chloride, disodium oxide and disodium sulfur. The next, similarity in hydrogen and halogen. See the chart. Element, molecular formula first column, and compounds with the metals and compounds with the non-metals. Elements with the molecular formula hydrogen H2, the compounds with the metal is a sodium hydrogen. And the compounds with the non-metal is a methane. Elements molecular formula chlorine Cl2, the compounds with the metal is a sodium chloride, whereas the compounds with a non-metal is having a carbon tetrachloride. Box close. Use your brain power. First, write the molecular formula of the oxides of the following elements by referring to the Mendeleev's periodic table. That is sodium, silicon, calcium, carbon, rubium, phosphorus, beryllium, boron, and Sn. Write the molecular formula of the compound of the following elements with the hydrogen by referring to the Mendeleev's periodic table. That is carbon, sulfur, bromine, arsenic, fluorine, oxygen, sodium, nitrogen, and chlorine. Next topic is a modern periodic table. The scientific world did not know anything about the interior of the atom when the Mendeleevs put forth the periodic table. After the discovery of electron, the scientists started exploring the relation between the electron number of an element and the atomic number. The atomic number in Mendeleev's periodic table only indicated the serial number of the element in 1930 AD. The English scientist Henry Moseley demonstrated with the help of the experiments done using X-ray tube that the atomic number Z of an element corresponding to the positive charge on the nucleus or the number of the proton in the nucleus of the atom of that element. This reveals that the atomic number is a more fundamental property of an element than its atomic mass. Accordingly, the statement of the modern periodic law was stated as follows. Periodic properties of elements are a periodic function of their atomic numbers. I repeat, properties of elements are a periodic function of their atomic numbers. Next topic is a modern periodic table, long form of the periodic table. The classification of elements resulting from an arrangement of the elements in an increasing order of their atomic number is a modern periodic table. The properties of element can be predicted more accurately with the help of modern periodic table formed on the basis of atomic numbers. The modern periodic table is also called the long form of the periodic table. In the modern periodic table, the elements are arranged in accordance with their atomic number. See the table 2.7. As a result, most of the drawbacks of Mendeleev's periodic table appear to be removed. However, the ambiguity about the position of hydrogen is not removed even in the modern periodic table. We have seen in the previous standard that the electronic configuration of an atom, the way in which the electrons are distributed in the shells around the nucleus, is determined by the total number of electrons in it. And the total number of electrons in an atom is the same as the atomic number. The relation between the atomic number of an element and its electronic configuration is clearly seen in the modern periodic table. In box, use your brain power. Position of the elements in the periodic elements. How is the problem regarding the position of cobalt and nickel? In Mendeleev's Mendeleev's periodic table resolved in a modern periodic table. Second, how did the position of the chlorine 3517 and chlorine 3717 get fixed in the modern periodic table? Question mark. The 17 is the atomic number as well as the 35 is the atomic mass. Can there be an element with the atomic mass 53 or 54 in between the two elements, chromium and manganese? Question mark. What do you think? Should the hydrogen be placed in the group 17 of halogen or in group 1 of alkali metals in the modern periodic table? Box close. Next topic is the structure of the modern periodic table. The modern periodic table contains 7 horizontal rows called the periods 1 to 7. Similarly, the 18 vertical columns in this table are group 1 to 18. The arrangement of the periods and the groups result into formation of boxes. Atomic numbers are serially indicated in the upper part of these boxes. Each box corresponds to the places for one element. Apart from these 7 rows, 2 rows are shown separately at the bottom of the periodic table. These are called lanthanide series and actinide series respectively. There are the 118 boxes in the periodic table, including the 2 series. It means that there are the 118 places for elements in the modern periodic table. Very recently, formation of the new elements was established experimentally, and thereby the modern periodic table is now completely filled. All the 118 elements are now discovered. The entire periodic table is divided into 4 blocks, as the S block, D block, D block and F block. The S block contains the group 1 and 2. The groups 13 and 18 constitute the P block. The groups 3 to 12 constitute the D block, while the lanthanide and actinide series at the bottom of the F block. The D block elements are called transition elements. A zigzag line can be drawn in the P block of the periodic table. The 3 traditional types of the elements can be clearly shown in the modern periodic table with the help of these zigzag lines. The metalloid elements lie along the border of these zigzag lines. All the metals lie on the left side of the zigzag line, while all non-metals lie on the right side. Next topic is a modern periodic table and electronic configuration of elements. Within a period, the neighboring elements differ slightly in their properties, while distinct elements differ widely in their properties. Elements in the same group show similarity and a gradation in their properties. These characteristics of groups and periods in the modern periodic table are because of the electronic configuration of the elements. It is the electronic configurations of an element which decides the group and the periods in which it is to be placed. Dear listeners, these are the self-explanatory broadcast for the self-study of a student. We are from Leader IAS and Yashas Institute. Myself, Professor Suhas Sargar. Now, in a box, characteristic of groups and periods. The characteristics of the groups and the periods in the periodic table are understood by the comparison of the properties of the element. Various properties of all elements in group show similarity and a gradation. However, the properties of element change slowly while going from one end to the other. For example, from left to the right in a particular period. Box close. Groups and the electronic configuration. Go through the modern periodic table in box table number 2.7 and write the names one below the other of the elements of group 1. Write the electronic configuration of the first 4 elements in this group. Which similarly do you find in the group their configuration? Which similarity do you find in their configuration? Question mark. How many valence electrons are there in each of these elements? Question mark. You will find that the number of the valence electron in these elements from the group 1, that is, the family of the alkali metals, is the same. Similarly, if you look at the elements from any other group, you will find the number of their valence electrons to be the same. For example, elements beryllium, magnesium and calcium belong to the group 2, that is, the family of alkaline earth metals. There are the 2 electrons in their outermost shell. Similarly, there are the 7 electrons in the outermost shell of the element such as the fluorine and chlorine from the group 17, that is, the family of the halogen. While going from top to the bottom within any group, 1 electronic shell gets added at a time. From these, we can say that the electronic configuration of the outermost shell is a characteristic of a particular group. However, as we go down a group, the number of the shell goes on increasing. In a box, do you know, uranium has an atomic number 92. All the elements beyond uranium with the atomic number 93 to 118 are man-made. All these elements are radioactive and unstable and have a very short life. Box closed. In another box, in the modern periodic table, the elements are arranged in an increasing order of their atomic numbers. Vertical columns are called groups. There are 18 groups. The chemical properties of the elements in the same group show similarity and gradation. Horizontal rows are called periods. There are in all 7 periods. The properties of element change slowly from one end to the other in a period. Box closed. See the picture of modern periodic table. Now next topic is the periods and electronic configuration. Can you tell, on going through the modern periodic table, it is seen that the elements of lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine, also neon, belong to the period second. Write down the electronic configuration of all of them. Second, is the number of valence electrons same for all these elements? Question mark. Is the number of shell the same in these? Question mark. Now, you will find that the number of valence electrons is different in these elements. However, the number of shell is the same. You will also find that while going from left to the right within the period, the atomic number increases by 1 at a time and number of valence electron also increases by 1 at a time. See the picture of new period, new shell for the potassium atom and argon atom. We can say that the elements with the same number of shells occupied by electrons belong to the same period. The elements in the second period, namely the lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon, have electrons in the 2 shells, potassium and lithium. 2 shells, that is a K and L. The element in the third period, namely the sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon, have the electrons in the 3 shells, that is K, L and M. Write down the electronic configuration of these elements and confirm. In the modern periodic table, electrons are filled in the same shell while going along a period from left to right, and at the beginning of the next period, the new electron shell start piling up. See the table 2.8. Now, the number of elements in the first three periods was determined by the electron capacity of the shell and the law of electrons octave. See the table 2.9, electron capacity of electronic shell. Can you recall what are the values of n for the shell K, L and M? Question mark. Second, what is the maximum number of electrons that can be accommodated in a shell? Question mark. Write the formula. Third, deduce the maximum electron capacity of the shells K, L and M. As per the electron holding capacity of the shell, 2 elements are present in the first period and 8 elements are in the second period. The third period also contains only 8 electrons due to the law of electron octave. There are the few more factors which control the filing of electrons in the subsequent period, which will be considered in the next standard. The chemical reactivity of an element is determined by the number of valence electrons in it and the shell number of the valence shell. The information on these points is obtained from the position of the element in the periodic table. That is, the modern periodic table has proved useful for study of elements. Dear listeners, these are the self-explanatory broadcasts from Leader IAS and Yashas Institute, Navi Mumbai, Maharashtra, myself Professor Suhas Sargar. These broadcasts are for the self-study of a student. Next topic is a periodical traits in the modern periodic table. When the properties of elements in a period or a group of the modern periodic table are compared, a certain regularity is observed in their variation. It is called the periodic traits in the modern periodic table. In this standard, we are going to consider the periodic traits in only 3 properties of element, namely the valency, atomic size and metallic non-metallic characters. Valency. You have learned in the previous standard that the valency of an element is determined by the number of electrons present in the outermost shell of its atom, that is, the valence electron. Now think about it. First, what is the relationship between the electronic configuration of an element and its valency? Question mark. The atomic number of beryllium is 4, while that of the oxygen is 8. Write down the electronic configuration of the two and deduce their valency from the same. Third, the table on the next page is made on the basis of modern periodic table. Write in it the electronic configuration of the first 20 elements below the symbol and write the valency as shown in a separate box. What is the periodic trait in the variation of valency while going from the left to the right within a period? Question mark. Explain your answer with the reference to the period second and the period third. Fifth question. What is the periodic trait in the variation of valency while going down group? Explain your answer with a reference to the group 1, 2 and group 18. Now, the symbol electronic configuration valency. Our next topic is the atomic size. Symbol, the K. Electronic configuration is a 2881 and valency is a 1. The next topic is atomic size. You have seen in the previous standards that the size or the volume is a fundamental property of a matter. The size of an atom is indicated by its radius. Atomic radius is the distance between the nucleus of the atom and its outermost shell. Atomic radius is expressed in the unit picometer, which is smaller than nanometer. 1 picometer is equal to 10 raised to minus 12 meter. Some elements and their atomic radii are given here. Elements and their atomic radius in picometer. Oxygen is having radius 66 picometer, boron is having 88 picometer, carbon is having 77 picometer, nitrogen is having 74 picometer, beryllium is having 111 picometer, and lithium is having 152 picometer. Now you will find that the atomic radius goes on decreasing while going from left to the right within a period. The reason behind this is as follows. While going from left to the right within a period, the atomic number increases one by one, meaning the positive charge on the nucleus increases by 1 unit at a time. However, the additional electrons get added to the same outermost shell. Due to the increased nuclear charge, the electrons are pulled out towards the nucleus to a great extent, and thereby the size of the atom decreases. Now in a box, you are seeing the elements and their atomic radius in picometer. Potassium is having atomic radius 231 picometer. Sodium is having atomic radius 186 picometer. Rubium is having atomic radius 244 picometer, etc. Box closed. Some elements and their atomic radii. Just now we listen. Now the next is use your brain power. Some questions for you. By referring to the modern periodic table, find out the groups to which above the elements belong. Arrange the above elements vertically downward in an increasing order of atomic radii. Does this arrangement match with the pattern of the group 1 of the modern periodic table? Question mark. Which of the above elements have the biggest and the smallest atom? Question mark. What is the periodic trend observed in the variation of atomic radii down a group? Question mark. You will find that while going down, a group of the atomic size goes on increasing. This is because while going down a group, a new shell is added. Therefore, the distance between the outermost electron and the nucleus goes on increasing. As a result of this, the atomic size increases in spite of increasing nuclear charge. The next topic is a metallic, non-metallic characters. Use your brain power. First, look at the elements of the third period. Classify them into metals and non-metals. Second, on which side of the period are the metals? Question mark, left or right? And third, on which side of the period did you find the non-metals? Question mark. It is seen that the metallic elements like sodium, magnesium are towards the left. The non-metallic elements such as sulfur, chlorine are towards the right. The metallide element silicon lies in between these two types. A similar pattern is also observed in other periods. It is seen that the zigzag line separates the metal from non-metals in the periodic table. The elements appear to have arranged in such a way that the metals are on the left side of these lines, non-metals on the right side, and metalloids are along the border of these lines. How did this happen? Question mark. Let us compare the characteristic element chemical properties of metals and non-metals. It is seen from the chemical formula of the simple ionic compound that the cation in them is the form from a metal while the anion from a non-metal. From this, it is understood that the metal atoms have a tendency to form a cation by losing its valence electron. This property is called electropositivity of an element. On the other hand, an atom of a non-metal has a tendency to form an anion by accepting electrons from outside into its valence shell. We have already seen that the ions have a stable electronic configuration of a noble gas. How is the ability to lose or accept the electrons in the valence shell determined? All the electrons in any atom are held by the attractive force exerted on them by the positively charged nucleus. Electrons in the inner shell lie in between the valence shell and the nucleus. Because of their presence, the effective nuclear charge exerting an attractive force on the valence electrons is somewhat less than the actual nuclear charge. Thus, the number of valence electrons in metal is small, in bracket 1 to 3, bracket close. Also, the effective nuclear charge exerting attractive force on the valence electron is small. As a combined effect of these two factors, the metals have a tendency to release the valence electrons to form cation, having a stable noble gas configuration. This tendency of an element, called electropositivity, is the metallic character of that element. See the pictures of periodic trains in elements. The periodic trains in the metallic characters of an element is clearly understood from their position in the modern periodic table. Let us first consider the metallic character of elements belong to the same group. While going down a group, a new shell gets added, resulting in an increasing in the distance between the nucleus and the valence electron. This results in lowering the effective nuclear charge and thereby lowering the attractive force on the valence electron. As a result of these, the tendency of the atom to lose the electrons increases. Also, the penultimate shell becomes the outermost shell on losing the valence electron. The penultimate shell is a complete octet. Therefore, the resulting cation has a spatial stability. Due to this, the tendency of the atom to lose the electrons increases further. The metallic character of an atom is its tendency to lose electrons. Therefore, the following trend is observed. The metallic character of elements increases while going down group. While going from left to the right within a period, the outermost shell remains the same. However, the positive charge on the nucleus goes on increasing when the atomic radius goes on decreasing, and thus the effective nuclear charge goes on increasing. As a result of this, the tendency of atom to lose the valence electron decreases within a period from left to the right. In brackets, see the table 2.10. The two factors, namely the increasing nuclear charge and decreasing atomic radius, as we grow from left to the right within a period, are responsible for increasing the effective nuclear charge. Therefore, the valence electrons are held with a greater and greater attractive force. This is called electronegativity of an atom. Due to increasing electronegativity from the left to the right within a period, the ability of an atom to overcome anion by accepting outside the electrons goes on increasing. The tendency of an element to form anion or the electronegativity is the non-metallic character of an element. Now use your brain power. What is the cause of non-metallic characters of element? Question mark. Second, what is expected trend in the variation of non-metallic character of element from left to the right in a period? Question mark. Third, what would be the expected trend in the variation of non-metallic character of elements down a group? Question mark. In a box, always remember, while going downwards in any group, the electropositivity of an element goes on increasing, while electronegativity goes on decreasing. Second, while going from left to the right in any period, the electronegativity of an element goes on increasing, while the electropositivity goes on decreasing. Third, larger the electropositivity or the electronegativity of the element, higher the reactivity. Gradation in the halogen family. The group 17 contains the members of the halogen family. All of them have the general formula X2. A gradation is observed in this physical state down the group. Thus, the fluorine are the gases, bromine is a liquid, while iodine is a solid. Collect the information and mail it. Internet, my friend. In box, inert gas element and uses of various elements. In box, read the following reference book from your library, Understanding Chemistry by C.N.R. Rao. Second, the periodic table book, the visual encyclopedia of the elements. Now in another box, do you know M plus H2H2O used to MOH2 plus H2? That is, a general chemical equation indicating the reaction of alkaline earth metal is given above. While going down the second group as the beryllium to the magnesium to the calcium to the Sr to next. The gradation in this chemical property of the alkaline earth metal is seen. While going down the second group, the reactivity of the alkaline earth metal goes on increasing, and thereby the ease with which this reaction takes place also goes on increasing. Thus, beryllium does not react with the water. Magnesium react with the steel, while the calcium and the strontium and the barium react with the water at a room temperature with increasing rates. That's all about this chapter. Dear friends, thanks for listening. These are the self-explanatory broadcast from Leader IAS and Yashas Institute, Navi Mumbai, Maharashtra for the students' self-study. Myself, Professor Suhas Sargar. Thanks for listening.